So welcome everyone, glad to see very familiar faces and new faces. I'm presenting on behalf of our research team at Rowan University, Jenna and Anthony, Ali and Zaid in the room. And our research is topology optimization based additive construction. First, we have to acknowledge the support from Department of Education through GAN grant. And GAN grant, if you don't know, is by Department of Education provides scholarship for US citizen and green card holder to pursue a PhD. Our research team, we have, as I mentioned, Jenna, Anthony, Zaid, and Ali as grad student, and we have actually, I will say, a squad of undergrad students because we have what's so-called Rowan University Clinic. So we actually have the students take 2 credits of research every semester, so we take advantage of that and actually help in workforce development. I want to ask a question. Every time I go present this lecture or this session, I actually ask, I have this slide, I ask, what's the difference between 1950 and 2021 century from this picture, construction-wise? Any difference you can spot?
Colored black and white.
Yes, black and white, right? So my presentation is not traditional one because I'm trying to differentiate between conventional construction where you have forming and you have to place reinforcement and cast, and what I called hybrid construction because we are not fully 3D printing, we're actually placing reinforcement and casting later. So it's kind of hybrid between what's called conventional and additive construction. So we're trying to work a lot on areas where we can have one set or one automated set for your element and actually additively construct with topology optimization. How many of you are familiar with topology optimization? So before I go to topology optimization, I want to get you guys familiar with what we are doing at Rowan University, from material, what equipment we have, the design process, the CAD process, and printing, and after that dive to topology optimization. So first, materials. So we develop in-house printing material using local source material in 50 miles away from Rowan University. And as you know, you have to check for printability, fresh hardened properties, and also shrinkage, especially for topology optimization. So we started as chronology here. This is what we started in fall 2022. We started with clay printer. So it was really rough print, and you can see here we also have good extrusion. In February 2023, we were able to really do very small beams, especially was really geared toward undergrad student. And after that, in October 2023, we were able to print arch-like structure, or what we call compression-only structures. And March 2024, actually, this month, we're able to scale it up. So our materials, we use cement, silica fume, we use slag or fly ash, but we have a good experience with our fly ashes. So most of our mixes include a good portion of fly ashes. We use 3 different types of sand, which is called fine, medium, and coarse sand, but this particular mix we are showing fine and medium. You can have here the chemical composition of all the solid materials. If you want to know particle size of medium, fine, and coarse, here are the percentage fine passing and particle size. And we reach very solid 10 KSI in 28 days, and actually in 3 days we got 5 KSI very comfortably. We are not using fibers at this stage, so our mixes are mostly mortars. We do have good interface bond that we reach, as you can see here. You can see the layer from the side, but we take advantage of heat and hydration, trapping moisture to actually fuse the layer together. This is part what I saw. I'm from Egypt, so I like to print pyramids. So I have successful extrusion, but you will see it looks fun actually when you fail. This was buildability failure. I think we printed out 25 layers on a slope. Very small nozzle. This nozzle was 6 millimeter nozzle. And you'll see now, as we go, there is actually buckling in the far 2 sides. And it looks really nice when failed, actually. You will see that even the other 2 sides, actually, because pulled out, actually filled. What we did, we reclaimed the same material, work it out, and print a cylinder out of it. So this was, if you see the cylinder, it's a cast of a pyramid. Equipment, we have a robotic arm mounted on a rail. This one, we have two systems. One is a syringe tube, when we fill the tube, and there is plunger that push the material out, and we also have the open system where we pump the material up to the nozzle. Design-wise, we did a lot of work on printing path. So we have one specimen where we printed longitudinally 7 filament and up to achieve 3-inch height and 3-inch width. We also printed transversally, so when you load it under 3-point bending, it will be perpendicular to the layers. And we also printed combination of both. If you can see here, actually, I don't know if you can see it or not, but this is actually how it looks like from inside. It's really fused. If you don't see the layer, if I'm cropping this area, you can think it's cast in place. But it's really fused because the way that we actually operate our printer. But you see here also, you can see traces of layers at the last one because we actually iterate between the two directions. This was related to the question that I asked last session, is the modulus of rupture. So we did a lot of testing to get modulus of rupture. You know that at the end, the printing was not exactly the same in dimension and cross-section, so we get the modulus of rupture for the beam one as around 10, or I would say 1,000 psi or 1 ksi. The second one, since we are loading perpendicular to the layer, was 0.678, and the last one is 0.934 ksi. So we actually try to use that to study the effect of printing path on the 3D printing structure. We know that concrete is very good in compression. So we actually created an arch, and this arch was basically a slab and an arch and the main arch. And we said if it's equivalent beam, we may have just 2 layers on top of each other. And if you go back calculate from modulus of rupture, you will get around 135 psi, or KSI, sorry, 135 pound or 0.135. When we load it, we have to restrict the ends from movement because it has to be hinges. So we actually, when we load it, we got 1.34 kips or 1,349 pound, which if you do a ratio, it's almost 10 times just by varying the printing path. So we came up with some really architecture and organic design where this one, for example, we have a top arch, a top slab, and some arches that load the main arches. And we have a lot of issues that we can discuss with you here related to the joints, some shrinkage, etc. And for undergrad, to make it really interesting for them, we asked them to choose some historical bridges with arch-like structures or arches. So we have one from Spain, one from Algeria, 2 from the US, etc. And they got informed by those designs. So from the CAD side, point of view, we do have, as I mentioned, compression on the structure. We try to load everything with compression. And we also have tension and compression structure where you have to have reinforcement. So this is one example of an optimized truss-like structure. I don't know if this can work. Yeah, so we used Onshape to do, or Onshape or Fusion 360 to do, to do the 3D model. We use Simplified 3D to slice it. And as you can see here, one of the structures that we have and the slicing and the speeds that we used. So printing. So this one is a tube that we printed with 6 millimeter nozzle. And I'm showing here the first quarter, second quarter, third, and last. And this one was done in 16 minutes. This is not a speed up print, so every layer was around 7 seconds. It was able to hold, the first layer was able to hold around 200 layers. We also were successful to print the pyramid, but we have some internal stiffeners to support the side. We also have the vases. We have for bridge columns, some design that Anthony is working on for seismic. This is the outer shell of it, and also we have connector columns. So this is actually verified for us that we have a very printable material. This is another project that we work on with geopolymer concrete. This is Ali's work, and he is working to optimize material for cementless material, no cement. So we are not using any cement, and this is a geopolymer, and we have a lot of additives that we add to make it printable. We run a lot of difficulties on this material. Sets very fast within 10 minutes, and we actually shattered like a couple of tubes in this process. So let's go back to topology optimization. So if you're familiar with additive manufacture of metals, I do work also in additive manufacture of metals. And the main two things in additive manufacture of metal, because the cost is very high of the process and material, they cannot afford printing bulky stuff. So they rely on two things, customization and optimization. So topology optimization is one approach, which is kind of shape optimization that use algorithm and numerical models to lay out material where is needed in a space based on a set of load, condition, and constraints. So for example, you have high compression, you lay more material on high compression. If you have low stresses, you try to subtract those. And it has so many benefits. You can see here one example from ANSYS showing a cantilever-like frame, and the topology optimization process running computational analysis to get a final product that will perform the same or even better than the original one. If you want to integrate topology optimization with additive construction, you will have benefit of overcoming labor shortage, and we can actually develop scale labor, good reduction in construction time, and cost saving because you are using less material. When you are using less material, you are using less material wastage, and also you reduce your carbon footprint. It creates some design creativity and ability to problem solving. And one advantage also is light structure, which is very beneficial for foundation, very beneficial for also seismic zones. But we have barriers. So it's very high, expensive computationally to achieve the best model. And you will have to have large equipment and 3D printers to do that. If you are not doing compression-only structure, you are doing tension and compression-only structure, you will have issues with reinforcement, and also it has to comply with existing specifications. So let's go see if it's actually suitable for concrete or not. Concrete, by nature, is cracked in tension, so the reinforcement can carry this tension reinforces. So if you can see here the hand drawing of the C line and the tension line, we are actually trying to envision a system where you print the compression line and you reinforce the tension line, and you have anchorage between them. So you can see here, this depth of the concrete actually cracked, and the main reason in reinforced concrete is to hold the reinforcement and have compatibility with the cross-section. We do source of optimization, which is shape optimization. This is our bridge beams or girders. You see the top flange and bottom flange carry the flexure or compression on top, tension on the bottom. Web also carry the shear. We try to work on compression-only structure and also work on tension and compression structure, and we're actually utilizing a lot of strut-and-tie methods to get the first guess on the model before we go to the numerical extensively. So back to the bridges. Here are some bridges. This is in Spain, this is in Tennessee, and I think this is in China. This is one, we actually decided to print most of them. This is 3 feet span and 1 foot depth, and the thickness was about 3.5 inches. And this is one for the printing process for one bridge. And this is a final print that we did last semester or early this year of those structures. We overcome some challenges. One of them is the one that has very cylinder element when you have a main arch and a slab, and because you have a stiffening at the joint, we actually observe, we printed like 2-3 times, we observed crack here, and we actually try to optimize the structure better. Here is the tested arch that we did before. And you can see here is this is the arch, and this is a slab, and how the layers are infused. We scaled it up, so we actually printed 6 feet by 2.5 feet and thickness of 1 foot. And this is a material in the market that we used. We didn't use our material because you'll have to prepare tons of them, and it's really tough, but we will also try to do that. So as a summary, with slight variation of printing path, you actually can achieve higher capacity because you load the layers on compression. The material actually is very good in printing. We are actually having more than 300 printing hours since last year. And we were able to print it out of 6mm nozzle and 8mm nozzle. And we also were able to print out of 1 foot last week. We have challenges on that, and we will start testing those structure really soon that we just printed. And the stiffening at the joint created cracks, which I believe was because the restraint that at the joint, not allowing the entire structure to shrink as a one unit. And this is 3D printing can be fun. I don't know if you can see this or not, but we printed different sizes, and one student with this as a funny stuff. But we printed also larger stuff, as I mentioned. We printed with 2K with this very nice Jenna did this model for different overhang and different slopes. So I wish you enjoyed my presentation, and I'm happy to receive any questions.